All right, so in this video, we're going to prove the second fundamental theorem of calculus, which deals with differentiating and integrating in the other order from the first theorem. So let me state the theorem. So let's see. Let f be integrable on AB for x in AB. So capital F is going to be basically you can think of it as an indefinite integral of f. So it's the integral from a to x of f of t dt. Then capital F is continuous. On the whole interval AB. And if little f is continuous at x naught in AB, then capital F is differentiable at x naught, and capital F, the derivative is actually little f of x naught. Okay, so this is saying that if you sort of first integrate the function and then differentiate it, you get back to the same thing that you had before, right? So I want to just say one thing about this. Okay, this what we have here is really the best way to think about indefinite integrals. Okay. Like an indefinite integral is really just like a definite integral where one of the bounds, one of the endpoints of the integration is like a variable. And so if you view this as a function as that endpoint moves, then you get another function which turns out to be an antiderivative of f. So antiderivatives are another way of thinking about indefinite integrals, basically. But either way, it's like, yeah, I mean, I think yeah, the concept of an indefinite integral is kind of like a little bit slippery sometimes, because if you get really used to thinking about finding indefinite integrals, then like you start to fall into this habit of just viewing integration as this like another one of these sort of symbolic operations where you just follow a certain algorithm and manipulate some symbols in order to arrive at the indefinite integral. And you're not really, it becomes easy to like forget what the symbols really represent, right? And like in analysis, that's kind of a cardinal error. I would say, that's like one of the biggest things that hinders people from properly understanding what's happening is just being too stuck in the mode of like thinking about integration as like this sort of algorithmic process where you manipulate functions of x and just do little substitutions and integrate by parts and stuff like that. It's deeper. It's a deeper concept than that. So anyway, let's go ahead and look at the proof. So basically, well, here, actually, let me sketch an idea. Okay, so here you can kind of see my attempt at sketching the basic idea of the proof, which is that if you're looking at, so f, right, if we're looking at the derivative, f of x minus f of x naught, f of x minus f of x naught is just basically, it's just the integral from x naught to x of little f, basically, right? So if you look at f of x minus f of x naught over x minus x naught, right, which is the expression that we want to sort of take the limit of to get the derivative, that's the same thing as the average value of little f on the interval between x naught and x. Oh, whoops, these are flipped. Hold on. So, oh, these are also flipped. So anyway, so since little f is continuous at x naught, this average value should tend towards little f of x naught because all of the values nearby, right, by the fact that it's continuous, all the values of little f nearby x at x naught are close to little f of x naught. And they get closer and closer as you get closer to little f of x naught. So the average value on this interval should definitely tend towards little f of x naught, at least intuitively. So that's kind of the basic idea of the proof. First, let's show that. So let's show capital F is continuous in the first place. So we know that, like, so we'll actually just show it's uniformly continuous. So by the same logic as what I just showed you, if you look at like capital F of x minus capital F of y, you get the integral from y to x. All right, let's flip the order of these. Then you get the integral from x to y of f, right? And so if you just put absolute values around this, then you can use the triangle inequality, so x to y of absolute value of f, and then this is less than or equal to the integral from x to y of b, where b, so say absolute value of f is less than or equal to b for some b. This is on AB. So B is just an upper bound on absolute value of little f on the whole interval AB, which has to exist because we're assuming little f is integrable, right? So that means that little f is bounded. So B is just some upper bound, and then this is just B. So this is if x is less than y. So this is B times y minus x. Okay, so if we pick delta to be epsilon over b, then for y minus x less than delta, we have f of y minus f of x is less than epsilon using this, right? So f is uniformly continuous on AB, but in particular it's continuous, which is what we were trying to prove, right? Okay, so then let's see. So now let's prove the part about the derivative, which is really what this this picture is about, showing that the derivative is little f. So right. So now let's show f prime of x naught is little f of x naught if little f is continuous at x naught. So, right, like I said, the expression, this divided difference, you can write as this integral f, right? So right, let's say we're looking at let's see, f of x minus f of x naught, right? Because we want to show that this approaches little f of x naught. So let's subtract little f of x naught. And then, of course, this is all going to end up in like absolute values. So we would have 1 over x minus x naught, integral from x naught to x f, minus f of x naught. So, you know, there's a trick here, which is like we would like to like combine these integrals or we would like to combine these terms somehow. And whenever you have like a constant and you're trying to you'd like to combine it with an integral, you can always like rewrite that constant as just like the integral of some other constant over the same interval here. So like this is the same thing as 1 over x minus x naught times the integral of x naught to x of f minus 1 over x minus x naught times the integral from x naught to x of f of x naught. Okay, because f of x naught is just a constant, right? So this integral is literally equal to like f of x naught times x minus x naught, and then that cancels out with this x minus x naught. So I'm just rewriting this term as an integral instead of as a constant. It's kind of a trick, but it also kind of makes sense if you think about it. Like what we would like to do is compare the difference between this integral and like if you just had f of x naught and it was like, you know, you had like a perfect rectangle, if the function was just flat here and it was equal to f of x naught, then like obviously the average value would be equal to f of x naught. So by comparing the true like area under the curve like this to this rectangle, and we should be able to hopefully show that like the difference in the area, which is just this tiny little, you know, thing, you know, if I blew this up, it would look like, you know, it would have like this, and then, you know, something like that. So we would want to show this. We would want to show that this goes to 0. Okay, which of course it does. So that's another, I guess, maybe another motivation for thinking about making this kind of modification. And then also it sort of works out nicely here that we can now, you know, combine these completely and factor out this 1 over x minus x naught. So we get, so, and I'm going to put everything in absolute values now. And then we have f of t minus f of x naught dt. And then using the triangle inequality and knowing, so let's just assume that x is well, all right, yeah, whatever. Actually, yeah, let's just keep, okay, so we can have this be in absolute values. And then we can move the absolute values inside the integral too, using the triangle inequality for integrals. So then we'll have f of t minus f of x naught dt, right? So then the idea is that we can make this be less than epsilon, yeah, make this be less than epsilon using continuity at x naught. So then, so, oh, sorry, this is also, okay, this should have a minus minus f of x naught. Right, so then this whole thing, becomes less than, right, 1 over absolute value of x minus x naught times absolute value of x minus x naught epsilon. And here it's like, okay, actually, when we do this, okay, there's like a slight annoying technical thing. So I'm going to put these arrows here, or maybe I'll put that in red. It's depending on whether x is bigger than x naught or smaller than x naught, these bounds might have to be flipped, because otherwise, if these were in the wrong order, this would actually be a negative number. So of course, this is not going to be less than this if this is negative. But as long as you keep the bounds in the correct order here, so depending on which one is bigger, just put that one at the top and the smaller one below, then you can make this be a positive number, and then this inequality will hold. And then no matter what, the way this works out is that if you replace this with epsilon here, the integral does become absolute value of x minus x naught times epsilon, because we already rearranged the bounds up here to be in the correct order so that you get a positive number, right? So it's going to be like either x minus x naught or x naught minus x, depending on which one of those two numbers is positive, right? But then that's the same thing as the absolute value of x minus x naught, okay? So that's how you get absolute value of x minus x naught here. And then these cancel out, of course. So this is epsilon. So that shows that this is less than epsilon. So pick here, we're just picking a delta such that for absolute value of x minus x naught less than delta, then we have absolute value of f of t minus f of x naught less than epsilon, right? That's what we just did over here. And so then by picking that same delta, it turns out that this whole quantity over here that we started with is also less than epsilon. And so that shows, right? So that shows that the limit as x approaches x naught of capital F of x minus capital F of x naught over x minus x naught equals little f of x naught as desired, right? Because that's the derivative. Yeah, so f prime of x naught equals little f of x naught. All right, so that's the second fundamental theorem. And in the next and final segment, we will look at some applications of, now that we have both fundamental theorems, we can do a little bit more stuff about like techniques of integration and stuff.